So now we're ready to continue our lecture regarding the order and field properties of the real numbers. So if you recall, last time we proved the multiplicative rule or the multiplicative law for the absolute values, but we needed a little glue proposition that wasn't really justified, but it's a relatively simple justification. So let's go ahead and justify that now. So proposition. The proposition is that if A and B are real numbers with A greater than 0, B greater than 0, then the product AB is greater than 0. Well, not only this, we knew this from the multiplicative property of the ordering system, but we actually wanted greater than or equal to, greater than or equal to, greater than or equal to. So the proof of this is relatively simple. We break it into the cases. The first case is, well, if A or B equals 0, then, of course, the product AB equals 0, which is, of course, greater than or equal to 0. Otherwise, we simply apply the multiplicative property. And this results in determination of the proof. The next result that we wanted to prove was that we could obtain a characterization of the absolute value being bounded by some real number. So suppose A is a real number and M is a real number that satisfies it's greater than or equal to 0. Otherwise, this inequality, of course, doesn't make sense. Then the absolute value of A is less than or equal to M if and only if minus M is less than or equal to A is less than or equal to M. So this is whenever you see an if and only if statement, you have to prove two directions. So the proof begins by starting with one of the directions. So let's prove. So first, we show that absolute value of A less than or equal to M implies minus M is less than or equal to A, and A is less than or equal to M. And that's just the definition of this simultaneous inequality. So there are two cases to consider because there are two cases for the absolute value sign. So first suppose, and note this is basically case 1, so you could break it down in terms of case. A is greater than or equal to 0. Well, by additivity, or the additive property of the order, we're going to have that minus M is less than or equal to 0. And so transitivity gives us the upper bound, or sorry, the lower bound, minus M is less than or equal to A. On the other hand, A greater than or equal to 0 implies that absolute value of A is equal to A, which is therefore less than or equal to M. And since these were the two inequalities that we wanted to show, we're done. Now the second case occurs when a is strictly less than 0, and therefore I have to replace with a negative. Well then, minus a is equal to absolute value of a, which is less than or equal to m. So when we add minus m and a to both sides of this equation, we'll get from the additive property that this is less than or equal to a. So we've established that first inequality. The second inequality, we want that the absolute value of a is less than or equal to m, but much like in the last case, we're going to have that, well, a is less than 0, which means that by assumption, m is greater than or equal to 0, and by transitivity, we have that a is less than or equal to m. So that was the first part. So now we have that absolute value of a less than or equal to m implies these two inequalities, and therefore this combined inequality. But now let's assume that we have the combined inequality, that is, it splits up into these two conditions, and now we go ahead and prove that the absolute value of a has to be less than or equal to m. So now suppose and generally you want to indicate the direction, and you can usually do that. Usually it's clear by supposing the particular hypotheses of one direction in the if and only if. So we're going to suppose that minus m is less than or equal to a, and a is less than or equal to m. Well, if a is greater than 0, then we again have absolute value of a is equal to a, and by this inequality we have that this is less than or equal to m, so we get the result. Again, we're using this case-based reasoning. On the other hand, if a is less than 0, then we're going to use this inequality. So we add minus a to both sides, and then we add n to both sides. And the additivity property gives us, so additivity gives minus a is less than or equal to m. So again, by the transitive property, we have absolute value of a in this case is equal to minus a. It's less than or equal to m. So the absolute value of a is less than or equal to m. By trichotomy, we've exhausted all the possibilities, and so we've completed the proof. So the final essential important ingredient for the absolute value is the triangle inequality, and so we need to prove this as our final act for the ordering principles. So the triangle inequality says that for all a and b and r, the absolute value of a plus b is bounded by the absolute value of a plus the absolute value of b. And this is used all over real analysis. So in order to prove this, it's really helpful to establish one simple claim first. And so let's go ahead and call that a lemma. So a lemma is going to, and we'll abbreviate it lem, but for now we'll call it lemma. So a lemma is used as a smaller result inside of a larger theorem, basically to break up the technical issues or the technical challenges of the theorem. So this lemma is going to say that if a is a real number, then minus a is less than or equal to the absolute value of a, and a is less than or equal to absolute value of a. So that seems pretty reasonable. The proof, so this is a sub-proof of this lemma. Well, obviously, the absolute value of A is equal to the absolute value of A. So by our previous theorem, we get to break this into the two different parts. So we get to remove the absolute value sign, and then we get a minus absolute value of A is less than or equal to A is less than or equal to absolute value of A. So, well, first of all, we have that minus A less than or equal to A is equivalent to so the inequality minus absolute value of A is less than or equal to A is equivalent to minus A is less than or equal to the absolute value of A. And you can establish that using additivity twice, right? So we add absolute value of A to both sides to cancel this out, and then we subtract off absolute value of A to both sides to cancel things out. And then clearly we have A less than or equal to absolute value of A via this inequality. And so we've shown that this holds, and so we can end the proof of the lemma. So this is going to make our lives a lot easier. So now we can break the proof of the triangle inequality into two cases. So case 1 is A plus B is greater than or equal to 0. So then we just remove the absolute value sign. Now we don't know the actual sign of the absolute value for A or B. We don't know if they're positive or negative, but we know that we can at least remove A plus B. But by additivity, this will be bounded by, since we have absolute value of A is a bound for A, and then we can apply the same additivity to get absolute value of A plus B, and the whole point was that this was equal to A plus B. The next case is that A plus B is less than 0. And so then we're going to have that A plus B will accrue a net negative sign, but then the distributive property gives us minus A plus minus B. And then we can go ahead and apply our lemma and the additive property to get the absolute value of A plus minus B. And then again, our lemma and additive property applies to the B term, and we obtain the result. This is an exhaustive list of the cases, and so we can conclude the full proof. So now we've developed essential theory that allows us to exploit the ordering properties and the algebraic properties of the real numbers. And we've established some very important consequences, and we've established the absolute value. But to finally do analysis, we need to pin down one final postulate for the real numbers that really distinguishes it from the rational numbers. So the rational numbers, they also enjoy having this ordering, they also enjoy having a field structure, but as we've seen, there are gaps all over the place. For example, pi or square root 2. So we're going to approach this property obliquely, and we're basically going to posit that every set which doesn't go off to infinity in the real line is essentially bounded by a number, and that number you can actually get your hands on. in, in theory it exists. And that postulate will provide us with all the powerful analytic tools to take limits, to perform derivatives, to carry out integration. So we have to define what we mean by a supremum. So this will be a somewhat long definition. So the first part of the definition is we need the notion of a bound for a set. So first we're going to let E be some subset of the real line. And we say that E is bounded above respectively below if there exists an m in the real numbers such that x is less than or equal to m, and for bounding below, m is less than or equal to x for all x in E. Finally, we can fix the notion of supremum. So a number, a real number, S, is called a supremum of E if script I, the first thing we need to have for the supremum is that S is an upper bound for E. So it has to be an upper bound. It has to be there. And the second thing is that S is a lower bound for the set of upper bounds of E. And so often we'll use the terminology that S is a least upper bound. So sometimes we call it least upper bound due to these two properties. So it's an upper bound, and it seems to be the smallest one. Later we'll show that, in fact, when the supremum exists, it has to be unique. There's only one possibility for it. Similarly, a number is called an infimum of E if 1 S is a lower bound for E, and 2 S is an upper bound for the lower bounds of E. And sometimes we use the terminology that this is the greatest lower bound. So now it might be helpful to look at an example of when we expect we could actually calculate, say, supremum. So for example, or an infimum. And also it's good to get some notation in. So let's suppose that E is equal to the open interval 0, 1. Then my claim is that the supremum, which is written sup of E, is equal to 1, and inf of E is equal to 0. So how do we show this? Well, first we need to show that 1 is an upper bound. So, and that's pretty clear from the definition of what it means to be in the open interval 0, 1. So x is in E if and only if. One might say this is the definition of the open interval. X is greater than 0 and x is less than 1. So 1 is an upper bound. And 0 is a lower bound. But then now we have to show that these are the least upper bound and greatest lower bound, respectively. So now suppose, so we'll do this for just 1. We'll show that it's the least upper bound, and 0 will follow similarly. So suppose M is such that x is less than or equal to m for all x in 0, 1. So then the goal is to show that, so our goal now, to show that it's the least upper bound, our goal is to show that then 1 has to be less than or equal to m. Well, we can proceed by contradiction. If m is less than 1, then we can cook up a number between m and 1 that'll be in the interval and therefore will contradict the fact that it's an upper bound. And so in particular, we can take the midpoint of this thing. So we'll have that m is less than m over 2 plus 1 over 2. And that comes by splitting up m into m over 2 plus m over 2 and then applying this. And then we'll also have that this is strictly less than 1. So now we have a number. So in particular, let's go ahead and assume that, so now we have a number. So technically this might not be in the interval because it might be below 0. But of course, if it were below 0, then of course we could cook up a number, just say 1/2, that breaks this rule. So without loss of generality, let's just assume that m is strictly greater than 0. Otherwise, we could easily break this rule. So now we've got a point that lives in our set E, 0, 1, but contradicts the fact that x is less than or equal to m, right? This inequality contradicts this fact. for all x in M. So we've assumed that M is less than 1, we've obtained a contradiction, and therefore we conclude that M1 must be less than or equal to M. So now there are a couple of notes that we should probably make. So by trichotomy, it's pretty simple to show that if you have two candidates for the supremum, they're actually equal to each other. The other thing is that our definition of the supremum essentially implicitly implies that E has at least some upper bound. And in fact, if it doesn't have an upper bound, then of course the supremum cannot possibly exist because it can't satisfy the first property. And a similar result holds for the infimum. Now, the next results that I'm going to discuss are with respect to the supremum. But they're going to equally apply in some measure to the infimum because of the reflection property. I'm not going to cover the reflection property, but you can look at the results in your text. Now, the first interesting property is that if E has a finite supremum and epsilon is greater than 0, then there is an x in E with sup E minus epsilon less than x, less than or equal to sup E. So that basically means that if I go just a little bit down from the sup, then I would have to have an x larger than that number. Otherwise, we would contradict the fact that we are sup. So the proof proceeds by way of contradiction. So by way of contradiction, what we're going to assume is that so we assume that epsilon is greater than 0 as given, and we assume that x is actually less than or equal to supremum of E minus epsilon for all x in E. But then sup E minus epsilon is an upper bound. Since it's an upper bound, then by definition of the sup of E, we have to have that sup E is less than sup of E minus epsilon. And then if we use the additive property a couple of times to subtract off the sups and add E's, or add epsilons rather, then epsilon is less than or equal to 0, which contradicts epsilon greater than 0. And we obtain the proof. Now, one nice thing that can be said about supremums for subsets of the integers is that the supremums actually are integers. And so this is an important theorem that allows us to carry out a lot of the simple manipulations that we want to derive once we assume or postulate that supremums exist for the real numbers. So now if E is a subset of Z and it has a supremum S is equal to supremum E, then our claim is that S is an E, and in particular E is a subset of Z, so S is also a member of Z. Well, by the previous theorem, if we let epsilon equal 1, which is of course greater than 0, then there is k in E such that S minus 1 is less than k, which is less than or equal to S, since it's supremum, of course, and therefore an upper bound. Well, by manipulating these inequalities, we can get that k plus 1 is a bound for S from this guy, and of course k is less than or equal to S. And so now we have S in between these two integers. And consequently, if L is greater than 0 for L an integer, then S is less than k plus 1, which will be less than or equal to k plus L. And so now we see that for every L greater than 0, S is a lower bound for k plus L. And so what does that tell us? This tells us that k plus L cannot exist in E. Otherwise, we would break the definition of the sup. For L exists in Z and L greater than 0. Now, since k plus L is not in E, we're going to then have that x is less than or equal to k for all x in E. Otherwise, we would have to have that, we would have an integer such that the integer is greater than k, and it is in E, but this is an exhaustive list of all the integers that are greater than that. And therefore, k is an upper bound. And by definition of the supremum, we have that S is less than or equal to k. Well, combining this with the fact that k is less than or equal to S, we have to have that k is equal to S. And of course, k therefore lives in E, and hence S is an integer. So we're now able to finally postulate what makes the real number line the real number line. So the postulate we're going to say holds for the real numbers is that for any subset of the real numbers which is bounded above, the quantity sup E lives as a number in R. And that postulate allows us to derive all the remaining important analytic properties of the real numbers. We can properly define limits, and eventually we can define continuity of functions, and then we can continue on from there. So this postulate has a number of consequences which are somewhat disconnected from the previous results we have for the supremum. So in the case of R, we have some pretty interesting things that we can say. So the first is the Archimedean property. So this is going to be a theorem, but it's pretty short. So the theorem, or the Archimedean property, says that, well, given A and B in the real numbers with, say, A is greater than 0, there is a natural number n such that B is less than n times A. So now we assume two cases for the proof. So in the first case, we're going to assume that B is strictly less than A. Now the proof is going to proceed again by cases. Typically we'll do a case-based analysis. So case 1, the simple case, well, we're going to just assume that B is less than A. Well, if B is less than A, then B is less than 1 times A by the identity property. That we have from the field axioms. And so n equals 1 will satisfy. If instead we have that A is less than or equal to B, then we note that A cannot be equal to 0 by trichotomy. A is strictly greater than 0. So 1 is less than or equal to A inverse B, multiplicative. So now that 1 is less than or equal to A minus B, thus, if we set E to be the set of integers bounded by A minus 1B, we have that E is non-empty. Obviously 1 is in there. And also E has A minus 1B as an upper bound. By our theorem regarding the supremum, the suprema of subsets of integers, we have that S is equal to the supremum of E is an integer, and in particular a natural number. Since it has to be greater than or equal to 1, which is greater than or equal to 0. And consequently, since it's a sup, we're going to have that A minus 1B is strictly less than S plus 1. If it were less than or equal to S plus 1, then S plus 1 would be an E, and therefore would be the sup, which would be a contradiction. So consequently, we have a minus b, a to the inverse b less than s plus 1. And by multiplicativity, we're going to then have that b is less than s plus 1 a. So n is equal to s plus 1 works. And in particular, it's a natural number, which concludes the result. So the last result that we really want to prove is the fact that if a and b are real numbers and a is less than b, so I can form an interval a to b, then there is a q, which is a rational number, that is strictly in between a and b. And so sometimes this is called the density of q in R. And this has all sorts of ramifications, but it's telling us something very important about the real number line. And in particular, any real number can be approximated arbitrarily well by a rational. That's a very important property. So first, since a is less than b, the additive property implies that 0 is less than b minus a. And the previous theorem, or the Archimedean property, where we're using b minus a in the place of a for the Archimedean property, and 1 in the place of b, gives us a natural number n with 1 is less than n times b minus a. So that's a great starting point, and essentially we're trying to find a fine enough grid of rational numbers to where we can slide in the rational number inside of Q that fits in between. So this n is indicating the scale at which we need to fix our grid so that we can find that number. So now the first thing to do is to assume that first our case 1 is that nb is actually an integer. And in this case, we're going to have the following inequality hold. Then NA is less than, so NA I get by applying the distributive property. So I apply distributive property to this inequality to get NB minus NA. I bring a minus NA over this side. I subtract off 1 from both sides, and I get NA is less than NB minus 1. And clearly, that'll be less than NB. Now, one of the consequences of this fact, and since n is a natural number, it's greater than 0, we can divide all of our sides by n. So the multiplicative property gives us a is less than nb minus 1 over n, which is less than b, and q equals nb minus 1 over n is a rational number. So that was a relatively restrictive case. NB was rational. But in order to make sure that we don't have to worry about that corner case, we had to check it out. So now this case is b is not an integer. Or sorry, NB is not an integer. So now in this case, our goal is defined. So our goal is find a k in Z with NA is less than K is less than NB. That's our goal. And then, of course, we can apply the multiplicative property to these two inequalities to get that A is less than K over N, and K over N is less than B, and we have K over N is a rational number. So that is our final goal. But we have to get our hands on that K. So what we're going to do is we're just going to set K and show that it does what it does. So set K to be the supremum over all integers less than or equal to less than NB, and not equal to. Obviously, they can't be equal to because in this case, NB is not an integer. And so K is going to be the supremum. Now, by way of contradiction, BWOC, if K is less than or equal to NA, then K plus 1 is less than or equal to NA plus 1. And then by our Archimedean property, we've shown that this is strictly less than N times B. And therefore, we have that K plus 1 is in the set for which K is a supremum, but of course K plus 1 is greater than K, and so we've contradicted the fact that K is an upper bound of this set. So we must conclude that NA is strictly less than K, and by our theorem, we know that K has to belong to this set since it's a set of integers. So we have K is also less than NB. So NA less than K less than NB implies, again by the multiplicative property applied twice, A is less than K over N is less than NB, and Q equal to K over N is a rational number, completes the result.